this module, we will be discussing chapter number 3, Matter and Energy. By the end of this chapter, you will be able to classify matter as element, compound, or a mixture. Also, you will be able to distinguish between physical and chemical properties, as well distinguish between physical and chemical changes. You will learn how to apply the law of conservation of mass. Also, how to identify and convert among energy units, convert between Fahrenheit, Celsius, and Kelvin temperature scales, and relate energy, temperature change, and heat capacity. Take a look around you. Everything that you can see in this room is made of matter, as the same way that everything that is around you now. Also, you can observe that everything has a different appearance, and this is because of the matter that it composes. Different kinds of matter are related to the differences between the molecules and atoms that compose the matter. That's why you can see different types of matters, because there are different atoms and also arrangement that produce a specific type of matter. The molecular structures, you can see here in this picture the molecules of water here on your left, and also the on your right, the atoms of carbons, graphite, that is part of the golf club. As you can see here, matter can be composed of just one type of atom, as here the carbon graphite, or also a combination of different atoms to produce a molecule, as here with water. Let's define matter. Matter is defined as anything that occupies space and has mass. Some types of matter, such as steel, water, wood, and plastic, are easily visible to our eyes. Other types of matter, such as air or microscopic dust, are impossible to see without magnification. But what is the composition of matter? Matter may appear smooth and continuous, but actually it is not. Matter is ultimately composed of atoms, submicroscopic particles that are the fundamental building blocks of matter, as we saw in the golf club before. In many cases, these atoms are bonded together to form molecules, two or more atoms joined to one another in specific geometric arrangement. So matter can be composed by individual atoms or by molecules. Recent advances in microscopy have allowed us to image the atoms and molecules that compose matter. Let's see another example of matter composed just by one type of atom. In an aluminum can, the independent particle is an atom of aluminum, as we can see here in this magnification of that piece of aluminum. So the composition is just atom of aluminum. That's the only type of atom that you may find in the aluminum can. In other hand, isopropanol, also known as rubbing alcohol, is an example of matter composed by molecules. This is the molecule of isopropanol. The molecule of isopropanol is a combination of carbon, that is the black sphere as we mentioned before, the white sphere is hydrogen, and the red spheres that are oxygen. So it's a combination of those three atoms in a well-defined structure. With the technique of scanning tunneling microscope, we are able to see the surface of matter on an atomic dimension. The blue bumps here represent individual atoms of nickel. Each of these are atoms of nickel in a surface of nickel. Also, this technique can be used to see the surface of molecules of living organisms, such as the DNA molecule. The DNA here is the yellow area in the picture, this one. And as you can see, is a double stranded. Here we have one strand of the DNA, and here we have the other one. So it's a double-stranded structure of DNA that it can be seen by the scanning tunnel and microscope. Let's talk now about the different states of matter. The common states of matter are solid, liquid, and gas. Matter can be classified according to its states: solid, liquid, and gas. For example, water exists as ice, that will be the solid, water, that will be the liquid, and steam, that is the gas. That's an example of the three different states of matter for the same substance. This is a representation of the three most common states of matter. Here we have the solid, the liquid, and the gas. As we can see at the molecular level, even though we are talking about the same molecule, we're talking here about water, H2O, it seems like they behave in different ways according to the state in which they are. In the gas states, here is the gas state, it seems like molecules are more random and they have more space between them. While in the solid one, that is one on the left here, water molecules seems more organized and steady. The molecules of the liquid have a little more freedom than the molecules of that are in the solid, but less freedom than the molecules of the gas. So in ice, the water molecules are closely spaced, and although they vibrate about a fixed point, they do not generally move relative to one another. They stay in the same position. The only thing that they can do is the vibration. In the liquid water, the water molecules are closely spaced but are free to move around and past each other. And in steam, water molecules are separated by large distances and do not interact significantly with one another. That's in the steam state. In solid matter, atoms or molecules pack close to each other in fixed locations. Neighboring atoms or molecules in a solid may vibrate or oscillate, but they do not move around each other. Solid have fixed volume and rigid shape. Ice, diamond, quartz, and iron are examples of solid matter. There are two types of solids: the crystalline solid, that are atoms or molecules that are arranged in geometric patterns with long-range repeating order, and also the amorphous solid, that are atoms or molecules that do not have long-range order. Here is a representation of a crystalline solid, and we can see that atoms or molecules occupy a specific position to create a well-ordered three-dimensional structure. And the other one is an amorphous structure where atoms do not have that long range order. As we can see here, they are more random, and here we have more like a well ordered structure in the crystalline solid. An example of the crystalline solid is sodium chloride, also known as table salt. The cubic shape of salt crystals is due to the well-ordered cubic arrangement of its atoms. Here we can see a large structure between ions of sodium and chlorine, okay, and they are well ordered, one chlorine, one sodium, one chlorine, one sodium in every way. So that's why the solid of salt looks like a cube, because the well-ordered arrangement of those ions in the structure. Now let's talk about the liquid. In liquid matter, atoms or molecules are close to each other but are free to move around and by each other. Liquids have a fixed volume because their atoms or molecules are in close contact. The liquids assume the shape of their containers because the atoms or molecules are free to move relative to one another. Water, gasoline, alcohol, and mercury are all examples of liquid matter. In gaseous matter, atoms or molecules are separated by large distances and are free to move relative to one another. Since the atoms or molecules that compose gases are not in contact with one another, gases are compressible. Remember when we saw the diagram before that the molecules of gas were really separate and they have a lot of spaces? So that's why they can be compressible. Gases always assume the shape and volume of their containers, as we can see here, all these balloons that are filled with air, and oxygen, helium, and carbon dioxide are examples of those gases. As we mentioned in previous slide, gas can be compressed because because since the atoms or molecules that compose gases are not in contact with one another, there is enough space between them so they can be compressed. This is a table that summarizes the properties of the three different states of matter. We have here the solid, the liquid, and the gas. At a molecular level or a molecular motion, when we have the solid molecules, we can see that they just oscillate or vibrate. They don't move all around as happened with the liquid and the gas. They are free to move. The spacing between the atoms or molecule in the solid, they are closer, and also in the liquid. While the gas, they are far apart. That's why they could be compressible. The shape is definite in the solid, is indefinite in liquid, and in the gas, they just take the shape of the container that they are. And the volume also is definite for the solid as well as the liquid, and for the gas is indefinite, the volume. And the compressibility, the solid and the liquids are uncompressible, while the gas is compressible. Now let's talk about the classification of matter. A pure substance is composed of only one type of atom or molecules. A mixture is composed of two or more different type of atoms or molecules combined in variable proportions. The composition of element is when the matter is composed of just one type of atoms. Element is a pure substance that cannot be broken down into simpler substances. No chemical transformation can decompose an element into simpler substances. You can find all the known elements in the periodic table. An example of this is a balloon filled with helium. Inside the balloon, the only matter that you will find is helium atoms, as we can see here, and they are basically moving freely all around and they have enough space between them, and they basically are constrained in this volume, and in this specific shape. The composition of compounds is when the matter is composed of just one type of compound. A pure substance composed of two or more elements in fixed, definite proportions. Compounds are more common than pure elements. Most elements are chemically reactive and combine with other elements to form compounds. Water, table salt, and sugar are examples of compounds. Compounds can be decomposed into simpler substances as different as the element. The element can't, but you can decompose the compounds to simpler substances. An example of a composition of compound is water. Water is a pure substance because it's composed only by molecule of water. Water is a combination of two elements, hydrogen and oxygen in a specific ratio, two atoms of hydrogen and one of oxygen. That's why water is H2O. Now, what is the difference between compound and a mixture? When matter contains two types of atoms, it may be a pure substance or a mixture. A compound is a pure substance composed of different atoms that are chemically united or bonded in fixed definite proportion. A mixture is composed of different substances that are not chemically united but simply mixed together. Let's see the following examples for mixture. Air and seawater are examples of mixtures. Air contains primarily nitrogen and oxygen, as we can see here in this figure. This is basically the composition of the air. Those are the most important, and the more that has presence in the air is nitrogen and oxygen. And seawater contains primarily salt and water. So, in the classification of matter, a pure substance may may be either an element such as copper or a compound such as sugar. Now, a mixture may be either a homogeneous mixture such as sweetened tea, or a heterogeneous mixture such as a hydrocarbon and water. Here I have also an example of another type of heterogeneous mixture. This is like a chicken soup. We can see carrots, we can see the chicken, we can see some celery around. So because you don't see like a whole body, you can define the different components of the mixture. That's a heterogeneous mixture. On the other side here, basically we have a jar of juice. This is homogeneous mixture. You can't um, see where is the sugar, where is the water. All of them is mixed together. So that's why this is a homogeneous. And this one is a heterogeneous mixture because you can see the ice and you can see the liquid. You can separate those two components of that one. So this one is a heterogeneous mixture, while this one is a homogeneous mixture. Let's see the following diagram for the classification of matter. Matter can be either a pure substance or a mixture. The pure substances can be classified as element or compound. Copper is an example of an element, and sugar is an example of a compound. On the other hand, mixtures can be classified as homogeneous or heterogeneous. An example for a homogeneous mixture is tea, while an example for heterogeneous mixture could be gasoline and water. So let's summarize what we have learned so far. Matter may be a pure substance or it may be a mixture. A pure substance may be either an element or a compound. A mixture may be either homogeneous or heterogeneous. And mixtures may be composed of two or more elements, two or more compounds, or a combination of both. So far, we have learned that we have different types of matter. In the same way, each matter has specific properties. One of them is called the physical property, which is the one that a substance displays without changing its composition. The other is known as a chemical property, which is the one that a substance displays only through changing its composition. Let's see some examples to try to understand the difference between these two properties. The characteristic odor of gasoline is a physical property. Gasoline does not change its composition when it exhibits its odor. The flammability of gasoline is a chemical property. Gasoline does change its composition when it burns. Let's talk now about physical change. The atomic or molecular composition of a substance does not change when the substance displays its physical properties. The boiling point of water, a physical property, is 100 degrees Celsius. When water boils, it changes from a liquid to a gas, but the gas is still water. It changed the appearance of water, but as a gas is still H2O. An example of a physical property is the boiling point. The boiling point is the temperature in which a liquid is transformed to gas, but the composition is still the same. Boiling is a physical change because it's the process to go from liquid to gas. The temperature at which this process occurs is a physical property, the boiling point. When water boils, it turns into a gas, but the water molecules are the same in both the liquid water and also in the steam, as we can see here. They just change their appearance, but H2O is still in the liquid or in the gas as steam. What is a state change? State change is a transformation from one state of matter to another, such as from solid to liquid, or solid to gas, or gas to solid, or gas to liquid, and they are always physical changes. Now, what happens in a chemical change? First, let's remember that in a physical change, matter changes its appearance but not its composition. When ice melts, it looks different, but its composition is the same. Solid ice and liquid water are both composed of water molecules, so melting is a physical change. Now, in a chemical change, matter does change its composition. For example, copper turns green upon continued exposure to air because it reacts with gases in the air to form new compound. This is a chemical change. The susceptibility of iron to rusting is an example of a chemical property. Rusting is a chemical change. When iron rusts, it turns from iron to iron oxide, which means that the composition of matter changed. How matter change in a chemical reaction? Matter undergoes a chemical change when it undergoes a chemical reaction. In a chemical reaction, the substances present before the chemical change are called reactants. Most of the time, we're going to see this arrow, and this arrow help us to see which one is the reactant. The one in the left are known as the reactant, and the substance present after the change are called the products. So here we have the reactants at the left of the arrow, and the arrow pointing to the products. Basically, this is like a template for the chemical reaction. The difference between chemical and physical changes is seen at the molecular and atomic level. In physical changes, the atoms that compose the matter do not change their fundamental associations, even though the matter may change its appearance. In chemical changes, atoms do change their fundamental associations, resulting in matter with a new identity. A physical change results in a different form of the same substance. A chemical change results in a completely new substance. Let's see the following example for a physical change. Push the button on a lighter without turning the flint. Sometimes you can listen to the gas escaping. The liquid butane vaporizes to gaseous butane. The liquid butane and the gaseous butane are both composed of butane molecules. This is a physical change. It transform from a liquid to a gas. So that's why it's just a physical change. Now, push the button and turn the flint to create a spark. This will produce a flame. The butane molecules react with oxygen that is in the air to form new molecules, the carbon dioxide and the water. So the liquid butane here, the butane is the composition of carbon and hydrogen. And this butane reacts with the oxygen to produce carbon dioxide, that is two carbon and an oxygen. So this carbon may be obtained from the butane, while the oxygen will be obtained from the oxygen of the air. And also it will produce water. Water is H2O. It will be a combination from the oxygen from the butane, and the oxygen of water comes from the oxygen of the air. So that's why you transform not just from liquid to gas, but also from butane to carbon dioxide and water, two new different compounds. So this is a chemical change. Why is it important to understand the physical changes? Because we can take advantage of that. Chemists often want to separate mixture into their components. Such separations can be easy or difficult, depending on the components in the mixtures. If we have a mixture of miscible liquids, in other words, that they can mix together, we can separate them by distillation, in which we heat the mixture is here in the boiling flask, we heat that mixture to boil of the more volatile liquid first. We then recondense that volatile gas here as a liquid in a condenser and collect in a separate flask, while the less volatile liquid stays in the boiling flask. So using distillation, this one um, use the property of boiling point. When the two liquid has different boiling points, the more volatile will boil first, and then the other one will stay here. So in that way, you can take that advantage from the physical change to separate the components of a mixture of two liquid. Now, if a mixture is composed of a solid and a liquid, we can separate the two by filtration, in which we pour the mixture. Here we have the mixture in this flask and put it here in filter paper that is in this funnel, and we pour that whole mixture through that filter paper. The solid will stay in the filter paper while the liquid will be collected in this beaker or in any flask. So also you take advantage of those physical properties. One is a solid, one is a liquid, to separate with filtration in this case, to have the solid in the filter paper here that is in the funnel, and the liquid will be collected in this Erlenmeyer or any other flask. Now, let's talk about the law of conservation of mass. There is no new matter. Matter is neither created nor destroyed in a chemical reaction. You just transform the matter to one thing to another one, to one compound to another new compound. In a nuclear reaction, significant changes in mass can occur. In chemical reactions, however, the changes in mass are so minute that they can be ignored. During physical and chemical changes, the total amount of matter remains constant. Let's see an example. Suppose that we burn 58 grams of butane in a lighter, and this one will react with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. The sum of the masses of the butane and the oxygen is 266 grams, which is equal to the sum of the masses of the carbon dioxide and water. In this chemical reaction, as in all chemical reactions, matter is conserved. Even though you are producing two different compounds and you start with two different compounds, the mass of the reactant always is going to be equal to the mass of the product in a chemical reaction. This is the law of conservation of mass. Now it's time to talk about energy, the second subject of this chapter. Energy is a major component of our universe. Energy is the capacity to do work. From physics, work is defined as a result of a force acting on a distance. The behavior of matter is driven by the energy. So understanding energy is critical to understanding of chemistry. Like matter, the energy is also conserved. The law of conservation of energy states that energy is neither created nor destroyed. The total amount of energy is constant. The energy can be changed from one form to another. And energy cannot or can be also transferred, from one object to another. You can transfer the energy in different ways, and we're gonna see and how they can transfer in a few minutes. And energy cannot be created out of nothing, and it does not vanish into nothing. There are different forms of energy. The total energy of a sample of matter is the sum of its kinetic energy, the energy that is associated with motion, and its potential energy, the energy associated with its position or composition. So these are basically the total energy. It will be the sum of the kinetic energy plus the potential energy. The electrical energy is the energy associated with flow of electrical charge. The thermal energy is associated with the random motions of atoms and molecules in water. And finally, the chemical energy is a form of potential energy associated with the position of the particles that compose a chemical system. Let's talk about the units of energy. The SI units of energy is joule, named after the English scientist James Joule, who demonstrated that energy could be converted from one type to another as long as the total energy was conserved. A second unit of energy is the calorie, CAL, the amount of energy required to raise temperature of 1 gram of water by 1 degree Celsius. A calorie is a larger unit than a joule. A related energy unit is the nutritional or capital C calorie. You maybe have seen this in whenever you see the nutrition tables and food or stuff like that. So this nutritional calorie, is equivalent to 1,000 of the little c calorie. So when we talk about the capital C calorie, we're going to talk about the nutritional calorie, and the one with the lower c, we're going to mention them or refer it as simple as calorie. The kilowatt is another type of unit of energy. The kWh is 1 kilojoule per second times 3600 seconds in an hour. This is a table with the energy conversion factors. 1 calorie is equal to 4.8184 joules. 1 nutritional calorie is equal to 1000 calories. And 1 kilowatt per hour is equal to 3.6 times 6 power 4 joules. So let's do an example of how we can use those conversion factors. A candy bar contains 225 calories of nutritional energy. How many joules does it contain? So we have 225 nutritional calories, and we want to represent this energy in joules. Let's do the solution map. So we need to go from calories, nutritional calories, to calorie, to then go to the joules. And to do this, we need two conversion factor. We know that one nutritional calorie is equal to 1,000 of calorie, and also we know that 1 calorie is equal to 4.184 joules. So we have those relations that we found in the table that we saw previously. So now we just um, do the mathematical process here. We multiply 225 times 1,000. And remember that we always need to put this conversion factor in a way that the denominator has the unit that we need to cancel. So here we have the nutritional calorie in the denominators to cancel this nutritional calorie. And this multiplication will give us the calories, but the next conversion factor, we must have the calorie in the denominator so we can cancel those calorie and we can stay with the unit of joule. That is the one that they are asking in this problem. So then we multiply 225 times 1000 times 4.184, and this basically is the result of the expression of energy in joules for 225 nutritional calories. The physical and chemical changes that we discussed previously are usually accompanied by energy changes. The release of energy during a chemical reaction is analogous to the release of energy that occurs when a weight falls to the ground. When you lift a weight, you raise its potential energy. When you drop it, you release the potential energy. For this reason, objects or systems with high potential energy tends to be unstable. A weight lifted several meters from the ground is unstable because it contains a significant amount of localized potential energy. Unless restrained, the weight will fall, lowering its potential energy. So, from a chemical perspective, systems with high potential energy have a tendency to change in a way that lowers their potential energy. Objects or systems with high potential energy tend to be unstable. Some chemical substances, such as the molecules that compose TNT, trinitrotoluene, have a relatively high potential energy. Energy is concentrated in them. TNT molecules tend to undergo rapid chemical changes that lower their potential energy, which is why TNT is explosive. Some reactions release energy while others absorb energy. The arrow represents the direction of how energy increase. So in this area, this is the lower energy, and here we have a higher energy. Let's say that the reactants have this amount of energy and that the products will have this amount of energy. So the products have less energy than the reactants. That means that during the reaction, somehow the reactants release that energy. And that's why the products are more stable because they have less energy than the reactants. This process is known as an exothermic reaction, where energy is released. Now, let's say that the reactant have this amount of energy and that the products have this amount of energy. Now the products have more energy than the reactants, which means that during the reaction, the reactants absorb that energy and that's why the products are less stable because they have more energy than the reactants. This process is known as an endothermic reaction, where energy is absorbed. As mentioned before, thermal energy is a type of energy. The atoms and molecules that compose matter are in constant random motion. They contain thermal energy. The temperature of a substance is a measure of its thermal energy. The hotter an object, the greater the random motion of the atoms and molecules that compose it, and the higher its temperature. Now, do not confuse temperature with heat. Heat, which has units of energy, is the transfer or exchange of thermal energy caused by a temperature difference. For example, when a piece of cold ice is dropped into a cup of warm water, heat, thermal energy, is transferred from the water to the ice. So there is a transfer of heat from one substance to another. The temperature, by contrast, is a measure of the thermal energy of matter, not the exchange of thermal energy. Talking about temperature, let's see the different temperature scales. Three different temperature scales are in common use. The most familiar in the States is the Fahrenheit scale or degree Fahrenheit. The scale scientists use is the Celsius or degree Celsius, and a third temperature scale called the Kelvin or K. On the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. On the Celsius scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius, while in Kelvin, water freezes at 273.15 degrees Kelvin and boils at 373.15 kelvins. The Fahrenheit and the Celsius scales differ in both the size and their respective degrees, and the temperature each calls zero, and both contain negative temperatures. Like this one, the Fahrenheit goes until minus 459 and the Celsius minus 273. While the Kelvin scales avoids negative temperatures by assigning 0K to the coldest temperature possible, that is known as the absolute zero. So the absolute zero for Kelvin is 0 Kelvin, while for the Celsius degree is minus 273.15, and for the Fahrenheit, the absolute zero is minus 459.7 degrees Fahrenheit. This is a temperature at which molecular motion virtually stops. There is no lower temperature. And finally, the Kelvin degree is the same size as the Celsius degrees. We can convert between Fahrenheit, Celsius, and Kelvin temperature scales using the following formulas. So by using these formulas, you can calculate basically between or from Celsius degree Celsius to Kelvin or degree Fahrenheit to degree Celsius. Our final topic for this chapter is the heat capacity. All substances change temperature when they are heated, but how much they change for a given amount of heat varies significantly from one substance to another. For example, if you put a steel skillet on a flame or a pot, its temperature rises rapidly. However, if you put some water in the skillet or the pot, the temperature will increases more slowly. The question is, why? One reason is that when you add water to the same amount of heat must warm more matter, so the temperature rises slower. The second and more interesting reason is that water is more resistant to temperature change than the steel because water has a higher heat capacity. The heat capacity is the quantity of heat, usually in joules, required to change the temperature of a given amount of the substance by 1 degree Celsius, also in kelvins. When the amount of the substance is expressed in grams, the heat capacity is called the specific heat capacity or the specific heat and has units of joules per gram per degree Celsius. Also can be expressed in Kelvin. Here is a list of values of specific heat capacity for several substances. Notice that water has the highest specific heat capacity on the list. Changing the temperature of water requires a lot of heat as compared to gold, to silver, to aluminum. We can use the specific heat capacity of the substance to quantify the relationship between the amount of heat added to a given amount of substance and the corresponding temperature increases. The equation that relates this quantity is heat is equal to mass times the specific heat capacity times the temperature change, where Q is heat, M is the mass of the substance in grams, the heat capacity, capital C, that is the specific heat capacity in joules per gram per degree Celsius for the substance, and the T, that is temperature. This symbol is known as delta, so the name of this symbol or representation is delta T, and the delta means the change in. So delta T means the change in temperature. So let's do an example. Gallium is a solid at 25 degrees Celsius and melts at 29.9 degrees Celsius. If you hold gallium in your hand, it can melt from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise its temperature from 25 degrees Celsius to 29.9 degrees Celsius? The specific heat capacity of gallium is 0.372 joules per gram per degree Celsius. So we have 2.4, we have the mass of gallium. We also have the initial temperature. Sometimes we're going to see expression of Ti, initial temperature, or T0, that is also initial temperature. And we also have the final temperature, Tf, 29.9 degrees Celsius. We have also the specific heat capacity for gallium. So that means that we need to determine the heat that has been transferred. Okay, we need to determine the heat that has been transferred in this process where your hand will melt this piece of gallium. So we need to calculate first the change in temperature. We need to subtract 29.9, the final temperature, minus 25.0. That's another important thing. Whenever you see the delta T or delta volume or delta pressure, always is the final minus the initial. So if delta V, it will be the final volume minus the initial volume. And this one is delta T, the change in temperature. So it's um, the final temperature minus the initial temperature. So that's why we subtract 29.9 degrees Celsius minus 25.00 degrees Celsius. So this will be equal to 4.9 degrees Celsius. Now we look for the formula, and we have the mass, we have the specific heat capacity, and we have the delta T. So we just substitute those values in this equation, and then we start to cancel the units, grams with grams. This is in the denominator, this one is in the denominator, so we can cancel this. The degrees Celsius, we cancel this one that is in the numerator, and this one is in the denominator, so we can cancel those units, and we stay with the joules. Okay, that is the expression or the units of um, the heat. Okay, the heat, basically the units of heat also are joules. So this is the amount of heat required to rise the temperature of the melting point. An additional 200 joules would be needed to melt 2.5 grams of gallium. Once it reaches the melting point, the delta H fusion is equal to 5.59 kilojoules per mole. So, in review, matter is anything that occupies space and has mass. Matter can exist as a solid, liquid, or gas, and solid matter can be either amorphous or crystalline. Classification of matter: we have pure matter is either an element, a substance that cannot be decomposed into smaller substances, or a compound, a substance composed of two or more elements in fixed, definite proportions. Mixtures are two or more different substances, the proportion of which may vary from one sample to the next. The homogeneous mixture having the same composition throughout, and the heterogeneous mixture with having a composition that varies from region to region. We also talk about the properties and change of matter. The physical properties of matter do not involve a change in composition. The chemical properties of matter involve a change in composition. In a physical change, the appearance of matter may change, but its composition does not. Remember the water. When you boil water, you go from a liquid to a gas. You change the appearance, but you still have water in the steam. So you have H2O in the liquid and also in the gas phase. In a chemical change, the composition of matter changes. We talk also about the conservation of mass. Matter is always conserved in a chemical change. The sum of the masses of the reactants must equal the sum of the masses of the products. We also talk about energy as well as the matter. The energy is conserved. It can be neither created nor destroyed. The most common units for energy are the joule, J, the calorie, small c, and the nutritional calorie with the capital C, and also the kilowatts hour, kWh. Chemical reactions that emit energy are exothermic. Those that absorb energy are known as endothermic reactions. Temperature of matter is related to the random motions of the molecules and atoms. Temperature is measured in three scales: the Fahrenheit, Celsius, and the Kelvin. And finally, the heat capacity is a temperature change that matter undergoes upon absorption of heat that is related to the heat capacity of the substance composing the matter. So this will be all for chapter number 3, matter and energy.